Today we'll discuss the beginning part of Learning Target 5C, which will focus all on particle line motion from a derivative standpoint. Now this will be a topic that we revisit second semester once we have learned about integrals, but today's video will focus on everything we can find out about particle line motion from a derivative standpoint. In discussing motion, there are three closely related topics that we need to have down, so this video will talk about the definitions of a lot of the setups of things, as well as do a small example at the end. The first concept we have is position, which is usually denoted by x of t, and position determines where the particle is located on the x-axis at any given time t. Now, the derivative of position is velocity, so we usually denote velocity with v of t, but anytime in a free response question, if velocity is not directly given, we actually have to make the connection first that velocity is the derivative of position. Velocity determines how fast the position is changing at a given time t, as well as the direction of movement. Acceleration is our third topic, and it is the derivative of velocity, or the second derivative of position. And again, on a free response question, if acceleration is not directly given, you have to connect back to what is given in the problem. So acceleration is the first derivative of velocity, or the second derivative of position. Acceleration determines how fast the velocity is changing at a given time t, and the sign of acceleration indicates if velocity is increasing or decreasing. So here we have the chain of the three topics, position, velocity, and acceleration, and we can go down this chain by taking a derivative. So the derivative of position is velocity, the derivative of velocity will be acceleration. Some other definitions that we have is initially. If we see the word initially in a problem, that would mean when time is 0. At the origin means when position is 0, or x of t is 0. At rest means the particle is not moving, so velocity would have to be 0. And to determine the direction of movement, if the velocity of a particle is positive, then the particle is moving to the right. If the velocity of a particle is negative, then the particle is moving to the left. And to find the average velocity over a given time interval, we divide the change in position by the change in time. So for example, down here at the bottom, if our time interval given is the time interval from A to B, then our average velocity would be the position at time B minus the position at time A divided by the difference of B minus A. Some other definitions that we have to deal with. Instantaneous velocity is the velocity at a single instance or moment in time. If the acceleration of the particle is positive, then the velocity is increasing. If the acceleration of the particle is negative, then the velocity is decreasing. In order for a particle to change directions, the velocity must change signs. These concepts are all very similar to our last unit where we talked about f-prime analysis and the ideas between extrema, increasing, decreasing, inflection points, and concavity. So for instance, when we talk about a particle changing direction and the velocity has to change signs, velocity is the first derivative. So if the first derivative were to change signs, that would be a local extrema. So a change in direction is very similar to a local extrema. We're just working in the context now of a motion problem. Similarly, since acceleration is the second derivative, if the second derivative is positive, then the velocity, the first derivative, would have to be increasing. And if the acceleration, which is the second derivative, is negative, then velocity, which is the first derivative, would have to be decreasing. Another topic that we'll talk about has to do with speed. Speed is the absolute value of velocity, so speed tells us how fast something is moving without regard to the direction of movement. Since we're taking the absolute value, we lose the sign of velocity, and the sign of velocity determines whether a particle is moving to the right or to the left. So speed just tells us how fast something is moving without regard to the direction of movement. And a common question that we could get asked about speed is if a particle is speeding up or slowing down. That would be equivalent to if speed is increasing or decreasing. So if velocity and acceleration have the same sign, either both positive or both negative, then the speed is increasing. If velocity and acceleration are opposite in sign, so one is positive and one is negative, then the speed has to be decreasing. Or we could say the particle is slowing down. Now we're going to take all these definitions and apply them to our first example down below. So in this first example, we have a graph of velocity that's given. I've labeled some of the time values along. So our x-axis here is actually our time, and our y-axis would be our velocity values. And we can see that we have the time interval from 0 to 15, and we're given that particle P moves along a straight line during this time interval. we're going to use the graph of velocity to answer the following questions. So in part A, we're asked, where is particle P moving to the right? And we also are asked to give a reason for all of these answers. So particle P is going to be moving to the right when velocity is positive. So I'm going to fill in our reasoning first. So here we're looking for where velocity is greater than 0. Since we're given a graph of velocity, that is anywhere where we are above the x-axis would be where velocity is positive. And then velocity would end up being negative anywhere that we are below the x-axis. So here, particle P is going to be moving to the right from the initial time frame here of 0 to 2, as well as from 12 all the way to 15. So I'm going to write that out in interval notation. So particle P is moving to the right on 0 to 2, as well as 12 to 15. Now we can actually include 0 and 15, so I'm going to change that first parentheses there to a closed bracket because at time 0 itself, the velocity is positive. It's actually up there at positive 2. Same thing at 15 as well. We end above the x-axis, so we can also include 15 in part of our time interval for the particle is moving to the right. Now in part B, similar question, but asks where particle P is moving to the left. Well, for particle P to move to the left, or for any particle, the velocity itself would have to be less than 0. Since this is a graph of velocity, we're looking for where we are below the x-axis. So that is going to happen from 2 to 8, and then from 8 to 12 as well. Now I'm not going to include 8 in my interval. I'm going to put open parentheses and not do the entire interval from 2 to 12, but from 2 to 8, taking out 8, and then from 8 to 12. And the reason being is at time 8, the particle is not moving at all. And that actually leads us to part C. So in part C, it says the particle is at rest when, this would be any time where the velocity is going to be equal to 0. So if we look on our graph of velocity, I'm looking for any points where we are on the x-axis. So that's going to happen at time 2, time 8, and time 12. So the particle P is at rest at time 2, 8, and then 12 overall. And we can correlate this to stuff that we learned about the first derivative test. Since velocity is the first derivative of position, when I look at a graph of velocity, I'm reading it very similar to how I would read a graph of f prime. So when we are asked where a particle P is moving to the right, that happens where the velocity is positive, but that would be where the first derivative of position is positive. That would be similar to where a function f would be increasing. And when we're asked where particle P is moving to the left, that is very similar to where we're looking for where f prime would be less than 0, so where f itself would be decreasing. And when a particle is at rest, we're ultimately looking for critical points of this graph because we're looking for where the first derivative, velocity, is equal to 0. And we would have 3 critical points on this graph at 2, 8, and 12. Now, not all of these will be a directional change because in part D, we're asked where does particle P change direction? That's only going to happen at time 2 and at time 12, because to have a change in direction, it means that the velocity has to change signs. So at time 2, 8, and 12, the velocity is 0. All that means is that the particle is stopped or that the particle is at rest. That doesn't necessarily mean that it changes direction. Think about if you're walking somewhere. If you start walking somewhere and you pause for a second, that doesn't necessarily mean you have to turn around. It just means you stopped for that instance in time, and then maybe you continue on in the same direction, or you realize you need to turn around and walk back in the direction that you came. So part C and part D, although they're similar, there is that subtle difference there on at rest is when the velocity is just equal to 0, and to have a change in direction, that would happen when the velocity itself changes signs. So part C is very similar here to our critical points from our last unit. And part D, where we actually have a change in the velocity, so a change in the first derivative signs, these would be our local extrema from our last unit that we would have. So when I read this graph of velocity, from time 0 to time 2, velocity is positive because we're above the x-axis, so the particle here is moving to the right. Then at time 2, the particle stops and also changes direction, since after time 2, the velocity is negative. Then from 2 to 8, the particle is traveling to the left. Then at time 8, the particle stops for a single instance in time, and then it continues on moving to the left because the velocity is still negative from 8 to 12. Then at time 12, the particle stops again and actually changes direction, since from time 12 to time 15, the velocity then is positive. Now in part E and part F, we're going to talk about where the particle is speeding up or slowing down. This is going to require us to not only know what's happening with velocity, but to also know what's happening with acceleration. And if I scroll back up here to the last two bullet points up above, when velocity and acceleration have the same sign, either both positive or both negative, it doesn't matter, then the speed of a particle is increasing. If velocity and acceleration are opposite in sign, one is positive and one is negative, then the speed is decreasing. These two statements right here are going to help us with parts E and F down below. Now we have velocity because that's the graph that we're given, but in order to get acceleration, the acceleration is defined to be the first derivative of velocity. Now if I'm looking for the derivative of a given graph, I'm ultimately looking for the slope of that velocity function that we are after. So if I start examining this from time 0 to time 4, velocity here has a negative slope. From time 4 to 8, velocity here has a positive slope. From 8 to 10, velocity has a negative slope. 10 to 13, velocity has a positive slope. And then from 13 to 15, the slope there of velocity is actually 0 because we have a constant line. So in part E, we're looking for where the particle is speeding up. This would mean that velocity and acceleration have to have the same sign. So I'm going to start by actually writing our explanation here. So we're looking for v of t, and instead of calling it a of t, I have to connect back to what I'm given. So I can't use a of t yet until I first make the connection that acceleration is equal to the derivative of velocity, and we're looking for where those two functions have the same sign. Now, it does not matter if they're both positive or both negative, they just need to have the same sign. I'm going to start with the scenario where they would both be positive. Now, for velocity to be positive, we are looking for where we are above the x-axis, and for the derivative of velocity to be positive, we're looking for where we also have a positive slope. Now, the only place where this graph is above the x-axis with a positive slope would be from 12 to 13. So that's the case where both velocity and acceleration are positive. Now, if we look for the case where both velocity and acceleration are negative, we're looking for first where we're below the x-axis, because that's where our velocity is less than 0. And then I'm also looking for where the slope of this graph would be negative. So that's happening from 2 to 4, as well as from 8 to 10. So at all three of those times, and I'm going to list them in order here, 2 to 4, 8 to 10, and 12 to 13, particle P is speeding up because velocity and the derivative of velocity, which is acceleration, have the same sign. From 2 to 4 and 8 to 10, both velocity and acceleration are negative because we are below the x-axis with a negative slope. And then from 12 to 13, velocity is positive because we're above the x-axis, and acceleration is also positive because we have a positive slope there. Now, if we want to figure out where the particle is slowing down, we're looking for the opposite signs. So either velocity positive, acceleration negative, or velocity negative, acceleration positive. So let's start with our reasoning here. So in part F, we're looking for v of t, and again, I have to make that connection, v prime of t, which is acceleration, have opposite signs. One of the functions has to be positive and one of the functions has to be negative. So let's start with the first scenario where velocity would be positive, so we're above the x-axis, and the slope, so acceleration, would have to be negative. That's going to happen from 0 to 2 because we're above the x-axis, so velocity is positive, but we have a negative slope, so acceleration is negative. And now if I look for the opposite scenario where velocity is negative, we're looking below the x-axis, but we want the acceleration to be positive, so we need a positive slope, which would happen from 4 to 8 and 10 to 12. So if we list those in part F, our particle is slowing down on 0 to 2, as well as 4 to 8, and from 10 to 12. And that's happening because velocity and acceleration have opposite signs, plural. So from 0 to 2 here, velocity is positive, but our acceleration here would be negative because we have a negative slope. From 4 to 8, our velocity is negative because we are below the x-axis, but our acceleration here would actually be positive because we have a positive slope. And the same thing is happening on 10 to 12. Velocity is negative because we're below the x-axis, but the acceleration is positive because we have a positive slope. Now graphically, if we look at this as an overarching picture, all of the green shaded places are where the particle is slowing down. Notice at all three of those places, the velocity graph is approaching the x-axis because the particle has to come to rest as it is slowing down. So it is eventually approaching a place where the velocity itself is 0, which would be all of our x-intercepts. If we look at all the places that are shaded in yellow, that's where the particle is speeding up. That's happening as we're going away from the x-axis. So from 2 to 4, 8 to 10, and 12 to 13. This is just one way that we can be asked a particle motion question where we're given a graph of velocity. We're also going to look at how this can be formatted from a table, an equation, and we're going to look at another graph of velocity as well when we start looking at examples together.